Let's talk about principal energy levels, sublevels, and orbital shapes. Our goals are to differentiate between orbits, which we looked at with Bohr's model, and orbitals. We are going to explain the sublevels that are found at each principal energy level, describe the number of electrons that are found in each sublevel, and then be able to use the periodic table to identify the order of filling for electron configurations. When we look at orbitals, we're looking at areas of probability of where an electron can be found. So rather than distinct circles around the nucleus, this is just an area where the electron might be found. With electron configurations, which tells us where electrons can be found, and they're necessary to help with predicting bonding, charges, and physical properties. This is what you might see. So our electron configuration might look something like this, where we have all of these numbers together. So this would be all of the electron configurations possible for if you were at the last element on the periodic table. Electrons are going to fill according to the principal energy levels and the subshells that are within each level. So let's go ahead and define those terms. So the principal energy level, this is going to correspond generally with the rows of the periodic table, and it's going to represent the general size of the orbital as well as the distance from the nucleus. It will, in general, also represent the general energy. The further away from the nucleus, the more energy that those electrons will have. And each principal energy level will contain a certain number of subshells. I'd like you to grab a blank periodic table. I'll have ones available for you to print, or you can even add to the periodic table that you have, but we'll be adding multiple things, so I think it's best to have a blank one. Alright, so here's an example of the blank periodic table. I just wanted to first note where our principal energy levels are. So our principal energy levels are along the side. They correspond with our periods or our rows. Sometimes we see this written as n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, and n equals 7. There are going to be a few exceptions and a few variations once we look at the sublevels, and we'll talk about how those principal energy levels are going to be different within each of our sublevels. Each principal energy level, which is represented by n equals 1, n equals 2, n equals 3, and so forth, they are going to contain sublevels. So this first one contains only one sublevel, which we name S. The second one contains S and P. The third one contains S, P, and D, and the fourth one contains S, P, D, and F. So what are these sublevels? The sublevels are going to be certain orbital shapes or clouds that represent the probability of where electrons are likely to be found. So this is where will the electrons be found. We have S, P, D, and F. When electrons are in orbitals at higher principal energy levels, so an orbital that or a sublevel at principal energy level number 4 is going to have electrons that are further away from the nucleus than a sublevel in principal energy level number 1. Each sublevel will contain a certain number of orbitals, and each orbital within the sublevel will be able to hold 2 electrons. Expanding on our sublevels a little bit, so again, each orbital within the sublevel can hold 2 electrons. We have 4 sublevels, so we have S, which is shaped a bit like a sphere, and it has 1 orbital, which means that it can have 2 total electrons. We have the P sublevel, which is shaped like a dumbbell. It has 3 total orbitals, and it has 6 total electrons that it can hold. The D sublevel, it has 5 orbitals, which means that it can hold a total of 10 electrons. And then the F sublevel has 7 orbitals and can hold a total of 14 electrons. If we look at an example of the shape for each sublevel, here's an example of sublevel S. So again, it can hold a maximum of 2 electrons, and we have 1 orbital within each sublevel. So in this example, we have 1s, which would hold 2 electrons. We have 2s, principal energy level number 2. Sublevel S can hold 2 electrons. And then here we have principal energy number 3, sublevel S, it can hold a total of 2 electrons. If we, like we were talking about earlier with the probability maps, if we had a dot representation of the 1s orbital, it would look something like you see on the left, and the shape of the 1s orbital is a sphere. So this will be similar for all of the orbitals that we look at and all of the sublevels that we look at. So our next sublevel is P. P sublevel orbitals are going to be shaped like dumbbells, and at each sublevel, so for each P sublevel, it can have 3 orbitals. So within this sublevel, we have 3 orbitals. So we have orbital number 1, 2, and 3. And each of these orbitals can hold 2 electrons maximum. So 2 electrons in this one, 2 electrons in this one, 2 electrons in this one. It can hold a total then of 6 electrons across this. Now, each of the P sublevels would actually look like this. It would be combined together. So we have 3 different orbitals where electrons can be found, and each of those orbitals hold 2 electrons. Our D sublevel orbitals, here are the different shapes. They are going to each have kind of its own shape, but have a shape and be in a different plane. Each of the 5 orbitals, again, can hold 2 electrons for 10 electrons total. So orbital number 1 can hold 2 electrons, orbital number 2 can hold 2 electrons, orbital number 3, 2 electrons, 4, 2 electrons, 5, 2 electrons, so that we have 10 total electrons. This would be combined into one, so all of these would be combined into the picture that you see here. So at one principal energy level that has a D sublevel, this is what it would actually look like. And then keep in mind that if it has the D sublevel, it also has the P sublevel, so you're going to have this combined with everything for the P sublevel combined with the S sublevel. So it gets really complex. The final sublevel is F. So these are the shapes of the F sublevel. And whenever we look at this, again, these would all be combined. Each of these 7, so we have 7 different orbitals here. So we have 7 orbitals. They can each hold 2 electrons. So it has a total of 14 electrons. For our summary again, I'll go back to this picture. So again, we're showing, look, we have our principal energy levels, which are N, and that represents our principal energy levels. Whenever we look at our principal energy levels, inside of each of them, we have certain sublevels where the electrons will be found. You can go ahead and copy this summary into your notebooks just as kind of a reminder and a summary. So principal energy level number 1 has only an s orbital. It has then 1 total orbital for a total of 2 electrons. In the second principal energy level, we have s orbitals and s sublevels and p sublevels for a total of 4 orbitals and 8 electrons. In the third principal energy level, we have S, P, and D sublevels, which means that we are going to have 9 total orbitals and 18 total electrons. In the fourth, we have S, P, D, and F, which means that we have a total of 16 orbitals available and 32 electrons. Now, the way that these fill is not necessarily going to be directly in this order, so we're going to go over that. But this gives you a good idea of why, whenever we talk about the Bohr model, sometimes you hear that the valence electrons, or the total electrons, is 2, 8, 8, 8, or sometimes you hear 2, 8, 18, 32. And this is why you see 2, 8, 18, and 32, which is really an accurate way to say how many electrons there are, but that gets a little bit more complex with how it fills. All right, so I'd like you to grab your periodic table where you were filling in it again, and you've written down the principal energy levels along the side that correspond with the rows. What we're going to do is we're going to go ahead and add in our sublevels, and so I'm just going to highlight them and color them in. But our sublevel S is going to be all of the alkali metals and alkaline earth metals plus hydrogen and helium. And so that will be, I don't know why that disappeared, so this will be our S sublevel. Note that we have 2 columns of the periodic table, which corresponds with the 2 electrons. So our P sublevels then are going to include our 6 elements that it would be, well, many elements that would be all grouped together here. So this blue area is going to represent our P sublevel. Now, with the S sublevel and P sublevel, they will have principal energy levels that correspond with whatever we see along the rows and on the side. So this would be 1s, this would be 2s, this would be 3s, 4s, 5s, 6s, and 7s. And this would be 2p, 3p, 4p, 5p, and 6p. And then 7p, which is not shown here. Okay, now whenever we look at our D is going to be our transition metals. And so that would be everything that is in here, plus these last two, because they pulled them out from there. So this is going to be our D sublevel, which is including 10 elements across, or 10 electrons. Now, with the D sublevel, what I want you to note is that the principal energy level is one level lower, so it's one lower than the row. So what that means is that this is going to be 3D, this will be 4D, and then this would be down here, you'd have 5D, 6D, or you could say 5D, 6D. Okay, and so that would be our principal energy level for our D sublevels. Our last one then are our F subshells and S sublevels. So that will include our lanthanides and actinides. That's pulling out from the periodic table here and here. And so this is going to be our F sublevel. And our F sublevel is going to be 2 lower than the row. So what that means is that for our principal energy level, this will be number 4, so it's in row 6 technically, but this will be number 4, and then this one will be number 5. Alright, so the last thing to mention with this is how does this relate then to the electron configurations and how electrons are going to fill. And the nice thing is that we can use the periodic table and just follow it along, kind of reading it like we would a book, and use this then to identify where are the sublevels coming in and what is the sequence of that. And so what we have is we have 1s1, and then we'd have 1s2. Then we jump down, we have 2s1, 2s2. Then we have go over to 2p1, so we have 2p1, 2p2, all the way over to 2p6. And then we come back down to 3s, so we have 3s1, 3s2, jump over 3p1 all the way to 3p6. And then we keep reading, so we go 4s1, 4s2, and now's where we get to our D. Now we get to our D sublevel. Again, they're one lower than the row, and so we have 3D1, 3D2, all the way till 3D10. And then we go back to our 4Ps. So then we have 4P1 and 4P all the way to 4P6. Again, keep reading like we would. 5S1, 5S2, 4D1, 4D2, all the way to 4D10. And then we go back to our fifth principal energy level, 5P1 through 5P6. Now keep in mind these principal energy levels are showing how far they are from the nucleus, as well as in general the energy level, but whenever we're filling our electron configurations, we fill them based on the Aufbau principle, which is based on energy. So 5s1, even though it is slightly further from the nucleus, it has a slightly lower energy than what the 4d subshell or sublevel has. So the electrons in the 4d sublevel have slightly higher energy than what we find in 5s, even though 5s sublevel is slightly further away. So the periodic table shows us the energy and how the energy level increases as we go through. All right, so we were at 5p6, now we're at 6s, 6s2, now we're going to jump down and we'll be at 4f1, 4f2, all the way to 4f14. And then we'll go back to 5D and continue through 5D10, and then we'll go to 6P and go through 6P6. Finally, we have 7S1, 7S2. We'll jump down. We'll have 5F and then through 5F14. Then we'll go to 6D through 6D10, and then 7P through 7P6. Now, whenever you get down to the F's and even to some of the D's, there's a little bit of exceptions and anomalies, but in general, this is how we'll follow the periodic table, and I'll give you some examples of exceptions whenever we talk more about electron configurations.